Now that we know about delta plots, we can use them to analyze real data sets. Let's go back to our logistic growth kind of data set here and use a delta plot idea. Before we use a delta plot, one thing we should maybe do is look at, are the time steps all the same? I mean, just by eye they are, but if we had a longer data set, we might want a more automated way of figuring that out. So here I'm doing delta t from one step to the next. Down here at the bottom, that delta t is using a blank cell that doesn't really mean anything, so we can just delete that. And here I can see that all the delta t's are the same. If I wanted a way to automatically check that, if I had 10,000 rows or something, one way I could do that is to look if the standard deviation of them all is 0. If the standard deviation is 0, that means they're all equal. So that's a quick way to check. Now that we've checked that all the delta t's are the same, we can go compute the delta biomass. And I'm going to say, okay, what's the change from here to here? I could put that either here or there. I could put on the kind of first row of the pair or the second row. I know we usually have a guideline that we only look on the current row and backward, so that would argue for putting it here at D9. But I'm actually going to put it here at D8. So it's like looking into the future by one row. And the reason I'm doing that is because when we do our dynamical system, the delta from one row to the next is on the earlier of the two rows rather than the later of the two rows. Another nice reason to do that is sometimes if you put the delta value on the later of the two rows looking backward, then you have to put kind of a blank here on the earlier of the two rows. And sometimes Excel gets confused if you have a column heading and then a blank and then a bunch of data, and it won't plot the graph correctly. So we're breaking our usual guideline of don't look into the next row, but for good reasons. And I'm going to fill that down. Seem to be getting reasonable values all the way up to here, but that one is trying to look a row into the future. It sees a blank, it treats it as a 0. That doesn't mean anything, so I'm just going to delete that one. And now that I have the delta biomass column, I can plot that as the y variable against biomass. So notice I'm not using the time column here. That's the way we did our delta plots before. So here's our delta biomass. We should really do a good job labeling this, right? Because it's a different kind of graph than we've been usually doing. So this axis is biomass, not time, and this axis is delta biomass. And now that we see that, we can say, what pattern is going on here? Certainly not linear, maybe polynomial. So we'll fit a polynomial, and that's a pretty decent fit. So then how can we use that to talk about what the carrying capacity might be and the growth constant? If we look back at our limited population growth formula, it was k times current population times 1 minus the current population divided by the carrying capacity. So that's definitely a parabolic sort of thing, so it makes sense here to fit a parabola. Here's the formula we get. This is a little interesting because when x is 0, you would usually say 0 animals means 0 growth. You can't have animals growing out of nothing. So it's a little weird that we have this non-zero coefficient intercept here. We could just say that's experimental error and ignore it. We could say, well, let me really force that to be 0. And we've never played with this set intercept button, but we can do that now. Set intercept to 0. And then that recomputes the coefficients to be the best fit for the data, assuming or forcing that intercept to be 0. So that's a modeling decision. I'll leave it up to you either way. I'm going to go back to this and just ignore that 6. And you can do some algebra, and I've actually done it here, but just kind of hidden it. Let me show it to you. To turn the trendline formula, ignoring the intercept term, into one of our equations or another one of equations. And remember, y here is delta biomass, x is biomass, not time. So that's all the algebra you can do, and you end up getting a carrying capacity of 645, which is one way to estimate it from this plot, and that's related to a homework problem. This didn't actually get the title I wanted. We should do a good job there. Okay, so here the intercept term ended up positive, which doesn't make any sense unless you have migration into the region, I suppose. It's possible for that to end up negative, which means that the parabola crosses the axis at a non-zero value here. What that can mean is that there's some kind of minimum population size, and if you go below that, then the population is actually going to shrink. It's going to have negative y value and negative delta values, and that's called the Ali effect. So this is the graph we've been working on with no effect from the Ali. I don't know who Ali was. It's possible that there's some minimum possible population below which you lose enough genetic diversity, or the animals can't find each other and you end up having the population die out, or kind of in the middle where it doesn't have that initial positive slope. That would be like exponential growth, direct proportion. So that's just a little bit of fun population biology for you. One other quick thing back here on the data set. Sometimes people say, oh, let's just extrapolate the biomass by maybe highlighting it all and doing a fill down. And Excel gives you numbers. That's interesting. What do those numbers mean? It's not really clear how it's getting it, but if you look at the graph, can you tell what happened? I had highlighted the whole original data set, and then the numbers it gave me look a lot like if you had done a linear regression through that data and just continued it on, and that's actually what Excel is doing. So if you give it a bunch of numbers that don't have an obvious pattern to them, like it's increasing at 7 at every step, it just does a linear regression using x values that are just linearly increasing by 1 every time, and then just continues that linear regression. The interesting thing is, you could say in some sense it does that when the data is nicely increasing anyway. If it's increasing by constant steps, then the linear regression will just keep increasing by constant steps. So it actually makes sense as a general way to think about how do you extend a series of numbers. Good job, Excel. But let's go back and erase all the non-real data values here, just so we don't leave it looking strange or with artificial data.